Hi, welcome to the first of many weekly quantum computing recaps. This week we have a lot of cool news about superconducting scalability and fidelity. We have new algorithms and ways to run chemistry on chemistry simulations on computers, and we have some more really cool news. So let's get into it. I'm Spencer, and this is the first weekly quantum computing recap. The first thing I want to talk about is a long-range coupler that IBM announced recently. It is a microwave photon coupler that goes about 1 meter, and it allows IBM to now entangle across their QPUs. So one of the big issues with superconducting qubits was how do you scale them? Entanglement across these are difficult. You have to, they have a cool honeycomb structure and or like a hex shape kind of thing. But the big problem of scalability isn't how you kind of arrange the qubits, it's how do you connect them and entangle them across larger systems. So this L coupler is going to do that. They're even developing some error correction codes with it, and you have to, keep that coupler incredibly cold as well because it is superconducting, and it transfers the microwave quantum state across. So that is a really big milestone for IBM and their scalability problem. Now the big issue that they're going to have to solve is error rates. Another cool update we have is a new algorithm that IonQ developed called QITE, Quantum Imaginary Time Evolution, and it significantly outperformed QAOA for various amounts of reasons. You have reduced circuit depth, so you have a bunch of high entanglement, and you're able to reduce the circuit depth in that way, and instead of having an expensive optimizer that's running, there are a series of equations that get solved that give you the next step for running, and that's faster than using something like a SciPy classical optimizer that has to perform gradients and do a lot of complicated calculations. The QITE algorithm is very cheap to run, performs extremely well, and they're able to model molecules a lot more efficiently than with QAOA. They even verified this algorithm on their Forte and Aria systems, and it showed a lot of promise. So I'm looking forward to seeing what comes out of QITE. Hopefully we can do some more chemistry applications. Speaking about chemistry, Quantinuum announced their quantum nexus platform, and they also added an InQuanto version 4, which is doing, again, chemistry. Maybe we'll see QITE being implemented on InQuanto, but this is a very cool, useful way for people to be able to run, developers or whatever. If you want to run some chemistry simulations, you can do that. With InQuanto, we can see that you can have a wide amount of gates, wide amount of different basis states, and it performs very, very well, just a little bit slower than C++. And no one will be wanting to write C++, right? Everyone pretty much writes Python. So the massive performance for chemistry, maybe coupled with the QITE algorithm, you could have some useful quantum utility soon, hopefully. Speaking about quantum utility, AWS announced their quantum Embark program, and this is a little bit different than Amazon Bracket, but in this case, they're going to be looking at what you're using, what kind of algorithms you're running, all those different things in your AWS cloud, and they will give you recommendations for oh, hey, this might run better on a quantum computer. We're not there yet, but the preparation to hitting quantum utility is here. Amazon's getting ready for that. And we can already see with Quantinuum and IonQ, with Oak Ridge, chemistry applications are coming soon. So AWS might be preparing for that. A really, really cool research paper, a little bit different than what we've talked about, is a work between Riverlane and Rigetti on creating a sort of error correcting structure. What they've done is they've corrected along the X and the Z bases, and I guess I'm not sure what they're doing about Y axis, but they are able to use gates in this structure to, what is that? to stabilize the different errors that come in over time from the qubits, and they're able to stabilize that well. Yeah, so I believe that they're using 84 physical qubits, and I thought they were having something around 12 logical qubits. And these logical qubits are really special because they're actually error correcting qubits. So hopefully you should have really, really long stability with the qubits here. And they're even using FPGA decoders because hopefully the amount of time it takes to, error correct and to measure in different bases isn't too long. You don't want to spend forever because then you might as well use error mitigation. So scalability is a big problem, and it's still something they identify here. Oh yeah, 84 qubits there. So another thing they did was have a lookup table for different, you read out this state or this corrected state. What does that mean for the actual state of the qubit? That issue has to be solved. There has to be a better way to do this because that won't scale to millions of qubits. But even for, short-term quantum utility, it should be fine to have a lookup table. And this is a very promising approach for error correction on superconducting qubits. So a lot of really cool news with superconducting qubits. Even coming up to the next one, Google announced AI that was able to identify and mitigate errors in their superconducting qubits. So this is really interesting because I wouldn't call it a error correction, but it's an interesting method for error mitigation. I think it's the better way to go for mitigating errors. They're so complicated to predict. You can have, heat, you can have vibrations, you can have particles randomly flying in. Well, I guess random particles you can't really predict, but there's so many different ways these errors propagate and interact with each other that trying to create manual algorithms that mitigate against that is not going to be very useful. I think AlphaQubit is definitely the right direction forward for error mitigation, and they saw amazing results, accuracy up to past 3 nines. So it's just really, really cool stuff for superconducting qubits. I think this past week showed a lot of promise for them. And finally, Microsoft is going to be launching a quantum computer. They've been working on it for a long time. Now they're partnering with atom computing, and they're using neutral atoms, which have a lot of the benefits of trapped ions, and also a lot of the difficulties, like with gate speed and things like that. So very accurate qubits, right? They have 24 logical qubits. So wow, yeah. I mean, you get over 1,000 physical qubits, but they're not going to have 1,000 qubits. It'll probably be a couple hundred logical qubits with that number. But in this system, they had 80 physical qubits creating 20 logical qubits. They were able to actually show that they were able to create working qubits by running the Bernstein-Vazirani algorithm. But this is also a big milestone forward, especially for neutral atoms. Running gate-based neutral atom computers is a challenge, and I'm glad that Microsoft's working with atom computing. I think that this is definitely trapped ions and neutral atoms are some of the best technologies for quantum, so I'm excited to see how this moves forward. And a totally new technology, which is very interesting. Physicists at ETH Zurich created the first fully mechanical qubit. Very, very interesting. They were able to, perform operations on it, apply, arbitrary pulses, weight, and readout measurements, and there's a high correlation between the theoretical and actual measurements. So having something mechanical on a sapphire chip, you do have to super cool it, but having something that is a mechanical oscillator, I think works well in the system because quantum computers are fully, analog systems. That if you're analog all the way down, maybe there's some benefits there. Maybe there'll be more opportunity for error correction, error mitigation, if you can tune everything well. Like Google has everything's tunable, and IBM has tunable couplers. this could even be something that's like a tunable qubit. So we'll see where that goes. Very interesting, a new way to think about qubits. And another interesting thing was RIKEN and Toshiba. They have a new coupler between superconducting qubits. And this coupler was actually designed via reinforcement learning. So they were able to create some sort of cost metric that an AI was able to design a more optimal coupler between the qubits. And they actually saw, this is incredible 2-qubit gate fidelity. You're getting, 99.92%. And if you've used superconducting qubits, you know that, what they report oftentimes when you actually use it, you can't hold entanglement for too long, but I think this is definitely the right direction to go. Even in a test situation, hitting 1.9 and then almost 2 nines for single qubit gates. Like, this is really amazing for how long it took other bigger companies to reach that level of performance with superconducting qubits. Like this situation here where they're using AI to optimize couplers, that is, I think, really, and here's a kind of picture of it. I think using AI to create the exact locations, and so complicated to predict where errors are going to propagate. If you can somehow encode all of this, you can use AI, and hopefully the goal is that we can have AI improve these qubits, couplers, whatever, scaling, error mitigation techniques, everything. With these better quantum computers, we can hopefully improve AI a bit, and there can be a bit of a feedback loop improving AI and quantum at the same time. So that was the weekly recap, the first one for the week of November 23rd. I hope you enjoyed, and I'll be making one of these every Saturday. Thanks so much for listening. My name is Spencer, and I'll see you next Saturday for the next Quantum Weekly Recap.